So what was Tony's big idea that Josh likes so much? Well, it's called partitioning. And it's a relatively simple idea that we'll spend a couple minutes getting to understand. So what you want to do is, given a sequence of items in any particular order, we want to pick first any arbitrary item, we'll call it the pivot, and then we're going to rearrange our sequence of items, in this case it's an array, so that after the rearranging process is done, all entries to the left of the item we picked, x, are less than or equal to x, and all the entries to the right of x are greater than or equal to x. And we'll say that x was just whatever item was in position I, the pivot position. Okay. So to see if that makes sense, what I'd like you to do is look at these 4 potential outputs of partition and tell me which ones are valid. Which ones satisfy this definition? So pause the video, think about it, and then I'll give you an answer. Okay, so it turns out the only one that's a problem is D. A, B, and C all obey this definition. I look at 10, everything over here is less than or equal to, everything over here is greater than or equal to 10. Now C, some of you might have felt a little weird about, because it seems like, why is this 10 here? But I'd like to note that partitioning is not sorting. It's fine that it looks like this, that 10 ended up to the left of the other 10. That's totally okay. This is still a valid partition. D is problematic because of the fact that the number 4 should not be to the right of 10, our pivot, wherever it ended up. Now note that the pivot, it changes positions in many cases, right? The I that you start at, sometimes it ends up in a different position, but it's fully okay. Sometimes it is the case that the pivot doesn't move after the partitioning process, but in this case, it turned out that all the valid partitions, I was not equal to j. But in general, it's possible that I could be the same as j. Okay, so what good is partitioning? Now that we understand what it is, you might say, well, it's not sorting, so what good is it? Well, we'll talk about that actually in the next video. Before we do that, I want you to spend some time trying to think about how you would actually go about partitioning an array. So this is what I'll call an interview question. This is the kind of question you might get at a job interview if you're applying for a computer science type internship or real world job. And the question is, okay, given an array of colors where the 0th element is white and the remaining items are red or blue, rearrange this array so that all red squares are to the left of the white square and all blue squares are to the right. In your algorithm, the only rule is it needs to run in theta n time. I don't care if you use extra space, however you want to do it. I mean, you can build binary search trees, whatever you want. You can use union find somehow. I mean, I don't think those things will be useful to you, but you can think of anything in the whole wide world that will take an array and it will make it into an array that has all the reds to the left, all the blues to the white, and the white item somewhere in between the red and the blue. Now, one quick note is that it doesn't matter what relative order. So at this example on the left, it shows what happens if you keep all of the reds in the same order. But on the right, we see an example where the reds change relative order. So instead of 3, 1, 2, 4, it's 3, 4, 1, 2. So it doesn't matter. Either way is fine. Use however much space you want, but do it in theta n time. That's your goal. Pause the video, think about it for a little bit, and then I'll spoil it with an answer I have in mind. Okay. So if you were a real life student at Berkeley, then and we were in lecture, I would take a few suggestions from the audience. I put the algorithm up on the slide we'd discuss, but I'm not going to do that here because, well, I'm just a video on the internet. But hopefully you have other people that you're talking to as you work through this class. I think this is a fun question to debate with others because there's a bajillion different ways of doing it. It's actually a really rich problem. So I'm going to tell you just one particular answer, which I think is the simplest, but not the fastest answer, which I'm going to call the 3-scan approach. So in this approach, what you do is you create another array, and then you scan through the array and copy all the red items to the first R spaces. So I see, is this red? No. Is this red? No. Is this red? Okay, great, copy it. Is this red? Yes, copy. Is this red? Yes, copy. Is this red? No, don't do anything. Is this red? Copy. Now, then what I'm going to do is scan for and then copy the white item. Though if you look at the problem statement, technically the 0th element is white, so that scan trivially finishes quickly. But this is a slightly more general approach that works no matter where the white item is. And then finally, we're going to scan through and find the blue items and copy those. So ultimately, we're going to do 3 scans, arguably 2 since the white item's already at the front. But this approach, hopefully you see that it's just a dead simple algorithm. And what's the runtime? Well, it's going to be theta n because we're just scanning through an array 2 or 3 times. Okay. So that approach, I think, is perfectly fine. There are faster approaches. You might have thought of some of those. Great. but this is just the one I did because I think it's the simplest to understand possible. Okay, great. So now that we understand that partitioning is first a theta n time operation, second, exactly how to do it, and third, what it is, not necessarily in that order, let's talk about how it could be used for sorting in this next video.